Hello friends, welcome to G-Centric. So in this lecture, we will see whatever concepts we have studied in the magnetically coupled circuit. We will see some of the question discussion based on those concepts. Okay, so we have studied ideal transformer in the previous lecture. A little bit more further version of it we will see over here. Okay, so in this question, basically, sorry, it's 249. 239 probably. Okay, so we have to find the relationship between voltages and current for ideal transformer. Okay, we have to find the relation between voltage and current. Before that, we will move over here. So we know that this is the ideal transformer where we have got primary, secondary, and the current should flow in this direction, primary, and secondary it should leave and enter to the load. Basically, primary means where we will excite the transformer. So that part is called as primary, and where load is connected we will call it as secondary part. Right? Now we have got 1:n turn ratio as well. If this is the polarity of the voltage or the excited voltage, then there will be plus and minus V1 voltage generated in the primary side, and plus and minus V2 is the generated voltage in the secondary side. So now what is the turn ratio? We will write V2 by V1 equal to I1 upon I2 equal to n by 1, right? So now if we separate this one, V2 by V1 is n, and we can take I1 by I2 is also equal to n, or we can write this one as I2 by I1 equal to 1 by n. Okay, so current will move in the opposite direction. Okay, so now we have the dot over here, right? Two dots are there. Wherever there is a dot, put plus sign. Okay, put a plus sign, and opposite to that, put a negative sign. Okay, so this is only for the turn ratio, whether we are seeing it as positive or negative. Okay, most of the cases we will neglect it in network theory, but in electrical machine this is important dot convention property. Okay, so now you see here, this is also plus, this is also plus. They both have same sign in the primary as well as secondary. So voltage will be positive. Okay, the turn ratio for the voltage will be positive. Next, coming to the current side. Okay, so we know that it is entering over here, right? Where there is dot, put a door and sit opposite to that door and see if the current is entering or leaving. So in this case, here it is entering and here it is leaving. So both are opposite. When both are opposite in the current, it will be positive sign. Okay, if they are of same polarity, then it will be negative. Don't get confused with the mutual effect and turn ratio. Turn ratio, it will move opposite. Okay, current will be opposite. Here it will be positive if they are dissimilar. It will be negative if they are similar. Okay, so coming to this A question. Now we have to find the relationship between both of them. Okay, so we have here V2 by V1 equal to n and I1 by I2 equal to n. Okay, so now we have plus sign, we have dot here, so put plus and negative. Here we have plus and negative. See, these both the signs are dissimilar, so this will be negative. Okay, the turn ratio will be negative. See the current now, this is entering. Okay, it is entering. Now this is also entering, right? So this will be negative sign. Okay, coming to this question number, V2 by V1 equal to n and I1 by I2 equal to n. Okay, so see over here, put a plus sign here, negative. Put a plus sign, negative. Again dissimilar, so you will have negative sign for the voltage. See the current, this is the door. Okay, put a door over here and put a door over here. Okay, sit opposite to here. Next, see, this is leaving current. Okay, and this is also leaving current. So this will be negative. Okay, coming over here, this is plus, this is minus, this is plus and minus. So V2 by V1 equal to positive n and I1 by I2 equal to, check over here, the current is leaving and here it is entering. Okay, the current is entering, so it will be positive n. Okay, so when they are dissimilar, it will be positive, otherwise it will be negative. So this is plus, minus, and this is plus and minus. Okay, so both are same, so we will get V2 by V1 equal to positive n and I1 by I2 is equal to, see over, it is entering, again it is also entering the door, right? So it will be negative n. Okay, so this is about the relationship between voltage and current. It's only valid for ideal transformer. Keep it in mind. Okay, so next we will solve some problem based on this concept. Okay, so now coming to this question number 240, we have to find reflected impedance and Zin. Okay, so basically this reflected impedance is nothing but the load from the secondary side will be reflected to the primary side. Okay, so and Zin is nothing but, we know, we will see it from here. So Zin will be equal to V by I. Okay, so if we take this current as I1 and this current as I2. Okay, so now to solve the, let us take this as ZR and this is Zin already given. Okay, so when we have to refer this over this side, we will apply KVL in both the loops and we will see what answer we will get. Okay, so now over here this is plus V equal to R1 I1 plus L di1 upon dt. Next we will see the sign over here, but because of I2 there will be a mutual effect in L1. Okay, so let us take this as L1 and L2 calls. Okay, so for this sign, check over here, the current is entering the door, here it is leaving. So it means it's a opposite sign, right? So it will be negative. So this is for the mutual effect, not for the turn ratio. When they are dissimilar in mutual, the current will be, the sign of the mutual effect will be negative. Okay, so now we will transfer this from time domain to frequency domain. So it will be Ri1 plus, so d by dt will be written as j omega. So this is L1, okay, minus j omega m I2. Okay, so this is equation number 1. Next, we will apply KVL in this loop. Okay, there is no voltage source, so it will be 0 equal to R2 I2. Okay, then we have got the effect for this one as ZL. Okay, this is plus ZL, then plus L2 di2 upon dt plus there will be a mutual effect due to current I1. So that is negative, right? Mutual effect is negative because currents are dissimilar ends. So di1 upon dt. Now we will rearrange this one, or it's we'll write it in the form of j omega R2 plus ZL plus j omega L2 I2. Okay, here we have missed I1. Okay, so this is I1 and minus m minus j omega m I1. Okay, so this is the equation. This, let us call this as equation number 2. Now to calculate the Zin, we want in the form of V by I1. So in this equation we have I1, but we do not want this I2. So we have to replace this I2. So which we can do it over here, right? So I2 will be equal to, this is j omega m, okay, we'll do it here, j omega m I1. Okay, so when we take over that side, and this is equal to R2 I2, this is ZL I2, okay, plus ZL I2 plus j omega L2 I2. So this I2 is replaced with j omega m I1 divided by R2 plus ZL plus L2, okay, j omega L2. Now we will put this in this equation. Ri1 plus j omega L1 I1 minus j omega m, and this I2 will be replaced with j omega m I1 divided by R2 plus ZL plus j omega L2. Okay, so now we will, j square is minus 1, minus and minus will become plus. So this j will be gone and you take this over here inside, it will be omega square m square. Okay, and this is, we want the ratio of I1, right? So I will take it over here, V by I1. Okay, so now whatever the equation you have got, this part is called as, so this is Zin, we will call this as Z1 and this we will call it as reflected impedance. Okay, so now if you observe, this is R plus L1, right? That we will call as Z1. See here, R1, we will take this as R1. Okay, R1, right? So this R1 plus L1, R1 plus L1 will give you Z1 of the primary side. If there is one more R2 also, you have to put here R2 plus R1 plus Z or L1. Okay. Next, this is the reflected impedance. See here, in this reflected impedance, it's related to the secondary part. So this omega square m square is this part. Okay. Then divided by R2. Okay. Then ZL and then L2. So all will come in the denominator part. So based on this concept, we will see this is like one of the derivation, and we will see the question based on this. So now we will solve the question based on the previous derivation. Okay, question number 241. We have to find basically, okay, find Z1 and Zin. So Zin and Zr. Okay, we have to find this one. Okay, so to find that, we know the formula. Okay, Zin is nothing but total voltage, total impedances over here. Okay, so this is nothing but 60 minus J100, and this is plus J20. Okay, this is the Z1 part. Don't take it as division. This is Z1 part plus omega square m square. We had it. Now we have here J phi m. Okay, so this is nothing but representation of the j omega m. So if you square this one, okay, you will get minus 1 omega square m square. But since there was one more minus, so it will be here plus as well. Okay, so it will be j phi omega, that is 5 square. Directly I can write it, divided by j40 plus 30 plus j40 ohm plus 80 plus j60 ohms. Okay, so this part is ZR and total is Zin. So this is how you will solve this question. Since this is complex variable, GATE won't ask this type of questions in this GATE exam. Okay, so you can solve it by yourself. Next we will come to that part. We have to find current I2. Okay, so the current I2 is over here. Either you can apply KVL or you can go with nodal analysis. So let me take here V1 and this as V2. So when I apply V1, okay, so before that we will take the turn ratio V2 by V1 equal to 2, which is I1 by I2. Okay, and from here we can take this V1 equal to V2 by 2, okay, or 2 times of V1 equal to V2, or in the current, since we want I2, so we will take I2 is equal to I1 by 2. Now applying nodal at V1. So V1 minus 10 divided by 2 plus V1 minus V2 divided by 2. Okay, and there is outgoing current I1 equal to 0. Okay, so we will rearrange this one. V1, that is 2V1. Okay, then we have minus V2 minus 10 equal to plus 2I1 equal to 0. Okay, so now we do not want this V2, right? So to do that, we'll apply nodal at V2 as well. Nodal at V2. Okay, so V2 by J2. Then we have plus V2 minus V1 by 2 equal to, we have incoming current I2. Okay, so it will be equal to I2. Okay, so now coming over here, this V2 can be replaced with 2V1. Okay, I'll replace it over here. Okay, 2V1, and this V1 gets cancelled. So from here we will get I1 equal to 5 amperes. Okay, so this I will put in this. I2 will be equal to 5 by 2, which will give me 2.5 amperes. Okay, so this was based on simple turn ratio and applying nodal. Okay, so now this is the end of this magnetically coupled circuit chapter. Next we will see the duality concept. So basically this magnetically coupled circuit is important for electrical machines, and in that especially for the transformers. Okay, so next we will see the concept of duality. Thank you.